Hi, Assalamualaikum everyone. Today I will explain how to solve a system of linear equation using Gaussian elimination. Let's go through it step by step. First, we need to identify the leftmost column that does not consist entirely of zero. We need to produce leading one at the top of the column by performing ERO. Second, perform ERO to produce zero at all integers under the leading one. Third, cover the top row with leading one. Find the leftmost column with a non-zero entry. Use an elementary row operation ERO to create a leading one at the top of that column. Fourth, begin step 2. Perform ERO to produce zero at all integers under the leading one. Last one, we need to cover the top row with leading one with the leftmost column with a non-zero entry. Use an elementary row operation ERO to create a leading one at the top of that column. Okay, so yang simplenya, first we need to create a leading one. Second, make zero below the leading one. Third, move to the next column and repeat the step. Okay, untuk example, dekat sini saya ambil x plus 2y plus z sama dengan 6, 2x tambah 5y tambah z sama dengan 15, 4x tambah 9y tambah 2z sama dengan 24. Okay, first step, kita buat the augmented matrix, iaitu masukkan dekat barisan ni, kita masukkan x, barisan ni kita masukkan y, barisan ni kita masukkan z, dan barisan ni kita masukkan yang belakang ni tadi. Okay, untuk dekat step tu pula, we need to perform ERO to produce zero at all entries under the leading one in the first column. Okay, maksudnya sekarang ni kita nak buat leading one and kita nak jadikan semua bawah leading one tu kosong. Okay, dekat sini saya ambil row tu yang baru sama dengan row 2 tolak 2 kali row 1. Okay, dekat sini kita nak jadikan second line ni depan ni kosong. Untuk yang bawahnya pula, saya ambil row 3 yang baru sama dengan row 3 tolak 4 kali row 1. So, kita dapat yang bawah ni pula. Kita dapat kosong untuk yang bawah ni pula. Okay, untuk step 3, cover the top row, find the leftmost column with a non-zero entry. Use an elementary row operation ERO to create a leading one at the top of the column. Okay, dekat sini pula kita nak buat leading one untuk row second. Kita nak letak leading one dekat sini. Tapi kan dekat sini dah ada sebab daripada sini lagi dah ada dah leading one. Jadi the second column has a leading one in the second row. So kita boleh skip. Okay, step 4. Begin again step 2. Perform ERO to produce zero at all entries under the leading one. Jadi kita ulang balik step 2 tadi. Kita ulang balik step ni untuk jadikan bawah ini pula kosong. Bawah leading one ni kosong. Jadi saya guna row 3 yang baru sama dengan row 3 tolak row 2. So kita dapatlah kosong dekat bawah ni. Step 5. Cover the top row. Find the leftmost column with a non-zero entry. Use an elementary row operation ERO to create leading one at the top of that column. Okay, lastnya kita nak letak leading one dekat sini. Jadi apa yang saya buat, dekat sini ada negatif. Jadi kita negatifkan balik negatif row 3. Jadi kita dapatlah satu kat sini. Jadi kita dah siap dah. Kita dah dapat leading one. Bawah leading one pun dah kosong dah. Okay, so step last, back substitution. Maksudnya, kita masukkan balik, kita nak dapatkan jawapan kan. Okay, daripada row 3, kita boleh dapat yang Z sama dengan 3. Satu masalah. Lepas tu daripada row second, kita dapat Y tolak Z sama dengan 3. Kita tukar-tukar tempat, dapat Y sama dengan 6. Lepas tu, daripada first row, kita masukkan X tambah 2Y tambah Z sama dengan 6. Okey, jadi tadi Y kita tadi berapa? 6. Z kita tadi 3 sama dengan 6. Masuk-masuk darab-darab dapatlah X sama dengan -9. Jadi inilah jawapan kita. Sekian, terima kasih. Harap semua faham.
Next, we continue with Gauss-Jordan elimination. So the function of Gauss-Jordan elimination is to turn the augmented matrix to reduced row echelon form. So here is the steps of Gauss-Jordan elimination, and I will explain further in the next example. Next, for further understanding, we look through the example. So the example here, we need to solve the following system of equation by using Gauss-Jordan elimination, where the system of equation is x plus y plus z is equal to 5, 2x plus 3y plus 5z is equal to 8, 4x plus 5z is equal to 2. The first thing we need to do is to turn the system of equation into the augmented matrix. So we write it as here 1 1 1 1 5 2 3 5 8 4 0 5 2 as the coefficient of all the variables. So the first row is R1, the second row is R2, and third row is R3. So the first step is to identify the leftmost column. So here is our leftmost column. So this column does not consist any zero, and we need to produce a leading one using ERO. As we can see, our first non-zero entry in the column is already a leading one. So the step 1 is complete. Continue with step 2, where we need to perform ERO. We need to produce all of the entries under the leading one is 0. ERO that we perform is to subtract R2, row second, with 2 multiplied by row 1. So 2 minus 2 is 0. So we will do the same thing for all of the entries in the row. So here is the result after performing the ERO. We got 0, 1, 3 and -2. Next, we perform another ERO for this row because we need all of the entries under the leading one is 0. So we subtract the third row with the first row multiplied by 4. So the result after the ERO, we got 0, -4, 1 and -18. As we can see, all of the entries under the leading one is already 0. So we can proceed with the step 3, where we need to cover the top of the row with the leading one that we already considered. So we find the leftmost column with a non-zero entry. So here is all 0. So we look at the next column. As we can see here, our non-zero entry is already 1. So we can proceed with step 4. To repeat the step 2, we perform ERO again to produce 0 at all entries under the leading one. So the ERO that we do is to plus the third row with the second row multiplied by 4. Now the entries under the leading one is already 0. Next, we continue with step 5. So we cover all of the row that we already consider its leading one. We find the leftmost column with a non-zero entry. So we need to create a leading one. From here, our non-zero entry is 13. The ERO that we use is to multiply the row 3 with 1 over 13. So we got 1 and -2. So by far, here is the result that we got from all of the steps that we have done. And then for the next step, which is step 6, we need to working upward, where we need to find the first leading one from below, which is here. So we need to make sure all of the entries above the leading one is 0, 2. So we need to do ERO again. So the first ERO that we do is to subtract second row with third row multiplied by 3, and the second one is to subtract the first row with the third row. For the last step, again, we need to ignore the row that the leading one we already considered, and we repeat step 6 for the remaining submatrix. So here we will ignore this row. So the leading one is here, and we need to make sure all of the entries above the leading one is 0. So we do the ERO again. So the ERO that we do is to subtract the first row with the second row. So the result here is 1, 0, 0 and 3. So the matrix is already in the reduced row echelon form. So from here, we can conclude that the solution for the system of equation is x is equal to 3, y is equal to 4, and z is equal to -2.
Now I'm going to explain how to solve a system of linear equation using the coefficient matrix method. First step is to solve the system using the formula AX equals to B, where A is the coefficient matrix, X is the column of variables, and B is the column of constants. And then we have to write the system in matrix form, which is AX equals to B. And then we have to check two things. First, we have to make sure A is a square matrix, where the row times column is in the form of n times n. And then to verify A is invertible via determinant, which the determinant must not equal to 0, or by row R reduction. And then we find the inverse of A, denoted by A inverse, using Gauss-Jordan elimination. After that, we multiply it with B and do matrix multiplication to find the values of the variables. And lastly, the resulting vector x gives the solution to the system of linear equation. Take for example, we are given this equation: 2x plus y equals to 5 and 3x minus 2y equals to 4. So how are we going to solve this system of linear equation? First, we identify these three variables. The coefficient matrix is 2, 1, 3, and -2. The variable is x and y. The column of constant is the remaining, which is 5 and 4. So we write it in a matrix form, which is 2, 1, 3, -2, x, y, and 5, 4. And the step 3 is to verify two things. First is to check if it is a square matrix, and yes, since it is a 2 by 2, it is a square matrix. And next is to check if it is invertible. We must find the determinant, which is the formula AD minus BC. We just times 2 times -2 minus 1 times 3. We will get -7, which is not equals to 0. So A is invertible. And then we can proceed to the next step, which is to find A inverse. This is the formula of A inverse, which is 1 over determinant A times the negated elements and switch elements. We will get 1 over -7 times -2, -3, 1 and 2. -2 times 1 over -7, we will get 2 over 7. -3 times -1 over 7, we will get 3 over 7. And the remaining we will get 1 over 7 and -2 over 7. So this is our A inverse. And step 5 is to multiply the A inverse with B, which is the column of constants, 5, 4. So to do that, we just multiply this row with this column and multiply this row with this column. So this is the calculation. 2 over 7 times 5 plus 1 over 7 times 4, we will get 2. And then 3 over 7 times 5 plus -2 over 7 times 4, we will get 1. So this is the resulting vector, 2, 1. And therefore, the resulting vector will give the solution to the system of linear equation where x equals to 2 and y equals to 1. That is all.
Everyone, so I will present the last method to solve system of linear equation, which is by using Cramer's rule. So in our poster, we show 3 steps, and I will explain further in the next slide. So for our Cramer's rule, there are 3 steps. For step 1, we need to write this system in matrix form, which is AX equals to B. So for A is the square matrix and is also the coefficient matrix. For our X is the column matrix, which is the variables, and B matrix is also the column matrix, which show the right side of the equations. So we reach step 2. Calculate the determinants d, dx, and dy. So before this, we need to construct d, dx, and dy. So for our d, it is from the matrix A, same as the matrix A, while dx, we need to substitute A1 and A2 with column matrix B. So you can see that C1 and C2 is inside this matrix dx. And this same goes to dy. In this matrix, we substitute the second column with C1 and C2, which is our B matrix column matrix. So after that, we calculate their determinants. So finally, we reach our last step, find x and y. So x is simply determinant dx divided by determinant d, while y is determinant dy divided by determinant d. So note that d is not equal to 0 to use this Cramer's rule, because in this formula, when d is divided by 0, is become undefined. And note that by definition, when there are n equations and n variables, and also the determinant d is not equal to 0, we only have unique solution. While determinant is equal to 0, that means that there will be infinitely many solutions or no solution in this case. So this is just a formula. So if there is a matrix 3 times 3, we need to construct dx, dy, and dz. And also the formula will be x, y, and z for 3 times 3. So here comes to the example. In this example, we have two equations, x plus y equals to 3 and x minus 1 equals to -1. In our step 1, we construct ax equals to b. So you can see that A is the coefficient matrix with the square matrix, 2 times 2. And so x is the column matrix and b is also the column matrix. Step 2, we construct d, dx, and dy. D is simply matrix A, and dx we substitute the first column with our B matrix, while dy we substitute second column with matrix B. And when it comes to dz, we need to substitute our third column with matrix B also in 3 times 3 matrix. So after that, we need to calculate their determinants. So for D determinants, we get -2, determinant dx -2 also, and determinant dy is -4. So we reach our last step for our Cramer's rule. X equals to determinant dx divided by determinant d. We get x is equal to 1, while y determinant dy divided by determinant d, which is equals to 2. So that's all from my presentation. Thank you.